Hello everyone, welcome back to the sequence of lecture videos on trigonometry, and in this video we're going to talk about the law of cosines. It is like the Pythagorean theorem but slightly modified. So let's say that we have a triangle where we know a few features of it, any three of the four, let's say. So there's an angle and three sides, and that's what we are going to consider in the equation. And the equation is similar to the Pythagorean theorem, so it's that the side opposite the angle squared is a squared plus b squared, the other two side lengths, but then we subtract 2ab cosine theta. So what you should remember is that if theta is the angle that we care about, then the two adjacent sides to it are the two sides that appear on the right-hand side of the law of cosines, and then the last side is squared and all by itself on the other side of the equation. So, like I said, it's like the Pythagorean theorem, but it has this 2ab cosine theta correction. It's to account for this possibly non-right triangle, or non-right angle. So it's good to work out exactly in which way it's like the Pythagorean theorem, so let's start with that. So if theta is pi over 2, which is to say that theta is a 90-degree angle, then since the cosine of pi over 2 is 0, then this entire 2ab cosine theta term cancels out. And so the law of cosines in this case is the Pythagorean theorem, c squared equals a squared plus b squared. Okay, so now for the remainder of this video, now that we've seen the law of cosines, we're going to go through a few basic sorts of questions that you could run into that the law of cosines can help you with. And what we're going to do is systematically look at what happens if we know any three of the four variables and then find the last one. So here's our first example problem. We have a triangle where the angle and the two adjacent sides are known, and we want to know what is the opposite side length. And let's say to 3 decimal places, because practically speaking, in the real world when you do trigonometry, everything is going to be approximate. So this is the law of cosines video, so let us apply the law of cosines. So the law of cosines says that the opposite side length squared is equal to the two adjacent sides squared minus 2 times the adjacent sides, each multiplied together, times the cosine of the angle. So I've already punched this all into a calculator, and without belaboring it, there it is. It turns out that if you have a 33-degree angle with 10 and 12 as the two side lengths, then the opposite side squared, remember it's still squared, has a length of 42.719. So what do we do to actually solve for x? Well, we take the square root. And in this case, notice that there's not a plus or minus out in front, and that's because when we have side lengths, they're positive quantities, so we do not need to worry about the negative square root. So I took the square root on the calculator, and I have this ... here to remind ourselves that it's when you're doing these intermediate calculations, it's better to take the square root of what's actually on the calculator rather than rounding to 3 digits the whole way through. So this is the correct answer when rounded to 3 decimal places. So what's another sort of problem that we could look at? So in this case, we've got 3 side lengths all known, but it's the angle that's unknown, and we want to figure out what is that angle in radians to 3 decimal places. So let us apply the law of cosines in this case. So the opposite side squared is the adjacent sides squared and added together, subtracting 2 times the product of the adjacent sides times the cosine of the angle. So I went ahead and plugged it all in, and then I simplified it to some degree, and we want to solve for theta, right? So let's, what will we do? In this case, what I did was I subtracted 36 from both sides, and also add 40 cosine theta to both sides. And that gives us 40 cosine theta is 41 minus 36, which is 5. And then we can divide by 40. Let me write that here. Div by 40. And then we can take the inverse cosine. So one thing to note here is that remember that the domain for the inverse cosine is from 0 to pi over 2. And so this is actually one of the cases where you can just use the cosine inverse function without thinking about it. It's going to be some positive angle measurement, and it will be in the right range. So I just punched this into a calculator, rounded it to 3 decimal places while making sure I was in radians mode. And so the answer in this case was 1.445. So what is another sort of problem that we could have? Let's say that we have an angle, and we know that the opposite side length of that angle is 2. And also we know one of the adjacent sides, but we want to know what is the length of the other adjacent side. So let's use the law of cosines. So we have 2 squared is 9 squared plus x squared minus 2 times 9 times x times cosine of 10 degrees. So in this case, let's see, 2 squared is 4, 9 squared is 81, and 2 times 9 is 18. So I've written in this way. And then I subtracted 4 from both sides. And that gives us a quadratic equation. So whenever you have a triangle and you're using the law of cosines and one of the side lengths that's adjacent to the angle is unknown, it's going to be a quadratic equation that you have to solve. So given that's quadratic, I use the quadratic formula here. So let's see. So we've got negative 18 cosine 10 degrees. So negative b is 18 cosine 10 degrees plus or minus the square root of b squared. I don't need the minus sign in there. I can put it. It doesn't really. So there could be a minus sign there, but I'm squaring it anyway, so it doesn't matter. It will give you the same result. And then minus 4 times a, which is 1, times c, which is 77, all divided by 2a. So that's that, and we simply have to calculate what those are. And it gives us 2 answers in this case. So, you know, it's a quadratic equation. You either get 0, 1, or 2 answers. There's no guarantee that these are actually achievable as triangles, but these are indeed all possible triangles, so there's not just a single value here. And here's what's going on. So when you have a side length of 9 and a fixed angle, you can either have the final line sort of going toward the base when it's drawn this way, or it could be going away. And in either case, that's a perfectly fine triangle, because we can see that, well, like really the only thing you have to worry about is if these side lengths end up being negative, or then it's just not possible. So, but we got 2 positive ones, and there we go, 2 triangles. And we can also see that it does make some sense. So in a triangle, the sum of any 2 side lengths has to be greater than the third side length. So 7.615 plus 2 is 9.615, which is bigger than 9. Great, that's possible. Oh, and also 9 plus 2, that's definitely bigger than 7.615. And over here, 9 plus 2 is 11. 9 plus 2 is 11, which is bigger than 10.111, so that's good. 10.111 plus 2 is bigger than 9, and of course 9 plus 10.111 is bigger than 2. Okay, so those were some examples of triangles involving the law of cosines and things you could solve for them. I'll see you in the next video.